Structural Analysis 2, Chapter 9, Force Method. Let's solve an indeterminate frame example. So in this example, we do have a indeterminate structure like a frame with support of pin at A and support another pin at D. So we have 1 degree indeterminacy in this structure and a 9 kilo-pound force applied at the corner B, like what you can see here, and also distributed of 10 kilo-pound per feet. It's uniformly applied at the top of our structure. So if we want to calculate the static indeterminacy of the structure, 3 times member plus reaction minus 3 numbers node plus the special condition. So if you do that, like internal hinge or so, that's a member 1, member, that's a 9 times member plus 4, which is the reaction pin AXA y, like by dx dy, 4 of them, minus 3 times j, that are like 1, 2, 4 nodes, and 0 special condition. It just gives us 1 degree of indeterminacy. If we just release the structure by AX, which it can easily roll to the left or right, it just easily freely moves to the left or right. That's a determinate structure. So one can say we can solve this problem once for determinate structure, like if these are all forces, like by summation of moment about, for example, point A goes 0, it just gives us a dy like 18 kilo. As soon as we have dy from moment equation, you can easily see this 24k 2 kilo-pound per feet intensity times the span of 12 feet, make it 24 at the center. So if dy is 18, the other part should be handled by ay, which is 6. So y is simply 3-fold of ay. As soon as we have that, we can release the support at A, which is a pin, and now it's like a roller support. So and we just consider AX like a redundant reaction. And then based off real structure, we can solve it by, and as soon as you apply that AX or R1, just moves by delta 1 like P for real structure. So we call that delta 1 P, delta 1 displacement due to actual force applied at the structure. So if we solve this determinate, and with this approach we just convert our indeterminate frames to a determinate frame, and then we can simply solve it by virtual work method for the determinate part. And at the same time, if you just consider the virtual part, if you have list all the forces from a structure, and you can consider the capital M like the reaction times small m, and with compatibility equation we'll solve based of virtual work approach once for calculation of delta 1 to the real load, and the other one delta 1 R for redundant reaction and compatibility, because at the beginning of our structure there was a pin here at A and there was no movement to the X and to the right. So at pin we have AX and AY. We just release AX to convert our problem to a determinate structure, then we replace the effect of delta 1 of redundant reaction, and they should be equal to 0 because there was no horizontal motion or movement or displacement at pin A. So let's approach our problem. If we divide our section to two vertical members like what you can see here and one horizontal member at the top, and then if we cut each of these members through and get the equation of moment, for example, this is a R2, M1 definitely is equal to 0 because the vertical component, if this is a ball support, ruler support, there is no AX, AY, which is 6, creates no moment at M1. So for the first part, real moment is equal to 0. If we cut the second part here, we have a 6 kilonewton applied here, and distance of x, calculate M2. And if we do so for M2, it just gives us M2 is equal to this equation, a negative x squared plus 6 times x. And also, if we cut the other part, it just the third member, it just gives us a moment, a real moment. M3 is equal to 9, negative 9 times x. So as soon as we have the real moment, we can remove all the forces on our structure, like in virtual. We are in virtual part for our determinate structure without. So as soon as you cut it through, like it just gives you a small m1 is equal to x because there is a virtual, or we apply a 1 unit force at support A, then calculate the moment there. So as soon as you do that, it just gives you m1 equal to x, m3 equal to a negative x. And at the same time, for the second member, it just gives you m2 is equal to negative 8 if you just cut it by this part and calculate the moment. As soon as we have the real moment for the our structure and we have the small m, we can combine them together. So these are the virtual moments, small m for each part, m1, m2, m3. And then the real moment, like we calculated at the very beginning, this is 0. So for this part, we have no nothing but by small m, capital M, or EI dx. Then you calculating the 1 times delta horizontal A, delta AH, delta HA, delta A horizontal. So, and if you just jot down the equation, I do recommend to have virtual moment, real moment, all the members 1, 3, 1, and it just because this one is equal to 0, just turns to give us 2 values. So that's a m to m2 negative 8 times this one, and m3 negative small m, m3 times capital M, which is negative 9x, and then integrated, it just gives you delta 1p displacement due to real load. It just gives you 2688 displacement of horizontal displacement at support A for our determinate structure, determinate frame. But we do know our problem is not fully solved yet because our frame is 1 degree indeterminate. So what to do next? So if you just consider delta 1r, which is a small m, capital M, this part stands for capital M. As soon as you calculate the small m to virtual load at the previous part, if you just simply multiply it by r, if you just simply multiply it by r, which is our redundant reaction, it just gives us the capital M. So we have a small m, we have capital M, and this time we want to calculate delta 1 reaction, delta 1 for our redundant reaction. So as soon as you do that, it just gives you delta 1 of is equal to small m capital M, which is just a reaction or redundant reaction times small m, and it just gives you a, for m1 we have m2, we have m3, so we have all three parts. So a small m x times r for the part 1, from 0 to 8, which is the height of each member, each vertical member, plus 0 to 12, from 0 to 12, and -8 times the reaction dx plus the third part, and it just gives you 3328 times reaction at 1 over, this is over 3 EI, because it just integration of x, that's x squared integration, and it just gives you x cubed over 1/3. So it just comes here. So then by using the compatibility equation, delta 1, because we have a real pin here, not the ball support. So we solve the problem by the effect of solving first for a determinate structure and replace pin by a ball support and solve the problem. And this is the answer for that part. Then compatibility equation, it just says delta 1 due to real force plus delta 1 for reaction should go 0, because at the original structure at A we don't have any ball, but we do have pin, which prevents the horizontal and vertical displacement. And if you equalize these two parts, it just gives you our redundant reaction, which is AX here. AX is equal to negative 2.42, and it just says our AX is pull outward force. So as soon as we have that one, solving the rest of the forces are pretty simple. If this is 9 and this is a 2.42, out of that it just gives us dx is equal to 6.58, because the summation of these two forces should cancel out this 9 kilopound force at corner B. And as soon as we solve that, we have all the forces on our indeterminate structure. Thank you. We'll solve more problems, indeterminate frames and beams in next videos. Thank you.